Drones have evolved over the years. It's exciting to see technology advance at a rapid rate. But aren't you curious to know the mechanics behind this flying wonder? You're in luck, because in this video, we'll explore the dynamics of drones, its design, its intelligent algorithms, and everything that makes it so unique in today's modern world. If you're just joining us, stick around, hit the like button, because you're in for an amazing ride.
Drones have evolved over the years and become perfect flying machines. Why are drones designed the way they are today? Why are they so efficient at moving so swiftly? In this video, we'll learn about the drone's mechanical design aspects, along with its electronics controller, sensors, intelligent algorithms, and even satellite technology. So, let's start a design journey, starting with a permitted drone and moving on to the most modern drone. Let's start with the simplest drone design, a single propeller design. One propeller drones provide enough lift force to keep the drone hovering in the air, but there is no way to control this drone. All it can do is go vertical and come down. Another issue is that this drone's body will keep rotating opposite to the propeller, which is a consequence of Newton's third law of motion. You can see the motor's stator supplies the necessary torque to the rotor part. According to the third law, this means that the rotor should give an equal amount of torque back on the stator. Since the stator is fixed to the drone body, this reaction torque will give the drone an undesirable spin. So why not use two propellers? This is certainly a possibility, and a company called 00 Robotics has made a serious attempt to develop such a drone. The fewer the number of propellers, the less energy the drone will consume, and the longer it can stay in the air. However, the main issue is that manipulating the drone to fly at high speeds and take sharp, quick turns requires a higher degree of control accuracy and stability. Let's hope that with the advancements in control algorithms, two-propeller drones will achieve a good stability one day. You can see that the blades of two propeller designs rotate in the opposite direction. This way, the motor's reaction torque gets cancelled and the undesirable body spin can be avoided. Three propeller designs are very rarely used. The main issue with these types of drones are the motor's reaction torque and gyroscopic precision. These issues create unnecessary complications in the design and algorithms. In the next variation, the four-propeller drones, or quadcopters, usually have an H shape or an X shape. Now, let's see how the quadcopters do the maneuvers by understanding the interesting force dynamics of them. To achieve hovering, the operator has to just make sure that the weight of the drone is exactly balanced by the thrust produced by the propellers. You can see the beautiful airfoil shape the propellers utilize to generate lift force. To achieve forward motion, the front propeller speed is slowed down while the rear propellers speed up. This will cause the pitch motion. Now, let's make all the force values the same by making the propeller speeds the same. Here, suppose you have balanced the vertical component of the resultant propeller forces with the weight of the drone. Even after this, there is an unbalanced horizontal force, which will make the drone move forward. A similar technique is used to enforce a drone's roll movement. Put simply, this movement is carried out by creating imbalanced lift force in the left and right pairs of propellers. A quadcopter's yaw motion is achieved in a unique way. In the beginning of this video, we learned about the motor's reaction torque and its effect on the drone. To avoid such undesirable spin, in quadcopter drones, one diagonal pair is spun opposite to the other pair. This technique cancels the reaction torque completely. However, if you want to yaw the drone or spin it, all you have to do is make sure that these reaction torques are not getting cancelled, which you can easily achieve by reducing the speed of the one diagonal pair. The reaction torque is proportional to the propeller speed. Eventually, a net reaction torque will occur, and the drone can achieve the yaw motion. Obviously, the quadcopter drones are the most stable. With the ability to move at high speeds and take sharp turns swiftly, they are used in almost every industry. Now, let's get into the brain of the drone. Suppose a drone is hit by a sudden gust of wind. The operator has to control and readjust each propeller speeds and rotation direction in less than a second. Otherwise, the drone may crash. This situation is difficult for a person to control by hand. These kinds of scenarios are where the most important part of the drone comes to the rescue: the flight controller. The flight controller can be thought of as a tiny, intelligent pilot sitting inside and navigating the drone through any difficult situations. It enables the operator to use simple controls like up, forward, yaw, etc., making the drone operation as simple as a video game. To achieve this result, the flight controller obviously needs a lot of input signals from various sensors. Welcome to the interesting world of drone sensors. You might be surprised to learn that the size of most of the sensors in a modern drone is comparable to an ant. To fabricate such tiny, super-accurate sensors, MEMS technology comes into play. They are microscale machines with actual moving parts. The most important sensors in this group are accelerometers, gyroscope sensors, and magnetometers. These three sensors are placed together in the IMU, Inertial Measurement Unit. IMU is the king of drone sensors. It measures acceleration and rotation. In this accelerometer MEMS sensor, as the drone experiences a force, movement occurs between the plates. The two plates placed next to each other have a capacitance. When the distance between the plates varies, the capacitance varies too. The variation in capacitance can easily be converted into electrical signals and fed to the controller for calculations. To achieve acceleration in all three directions, we will require a 3-axis accelerometer. When we include gyroscopes also in the unit, along with the force values, we can measure the rotations in different planes. A MEMS-based barometer sensor is used to determine the drone's altitude. Now, the flight controller or processor should make the right use of all the signals these sensors collect to make correct decisions. However, before going into the processor piece, how can we make sure that the signals sensors produce are accurate enough? Noise, for instance, can affect a sensor's accuracy. Some reasons for noise are defects, interference by the mechanical vibrations of the drone propellers, and magnetic interference. Modern drones use a technique called sensor fusion to overcome this issue. For example, a GPS sensor, along with the IMU, can provide a basic altitude information of this drone. However, we can make this measurement super accurate if we integrate radar technology also into this. This is sensor fusion, different sensors working together to produce more accurate measurements. With these accurate signals, we can get into the decision-making part of the drone, the control system part, which includes the control logic. The control logic is the algorithm that reduces the error further and makes decisions. One such algorithm is the Kalman filter. The KF algorithm reads the past and present data to know the state of the drone and utilizes its logic for GPS navigation, driving back home, and any other such cases. Or, in this case, stabilizing the drone after the disastrous effect of winds. Eventually, the same KF algorithm fed in the processor, having logic gates and transistors, etc., make smart decisions to control speeds of BLDC motors. Yes, just by controlling the speeds of the 4 BLDC motors in a smart way, the quadcopter drone can face any challenging environment. Currently, a company called DJI is one of the leading companies in the consumer drone market. They use advanced flight control algorithms, dual IMUs for more reliability, and vibration dampening systems to reduce errors in sensor output. Sophisticated algorithms are one of their keys to success. On the other hand, compared to DJI, companies like Parrot, Autel, and Unique don't have as much market in consumer UAV drones. These drones lack the refinement and fitness you get with DJI's drone. We already saw how the smart control of the BLDC motors by the Kalman filter algorithm ensures the drone a stable and happy flight. Power required by these BLDC motors, electronic circuits, antennas, and sensors are supplied by a lithium-ion battery. The drone receives the control signal from the user using the common radio frequency technology. The range of communication can be between 1 to 2 kilometers for a consumer drone. Now, an interesting question. What if the drone accidentally travels out of this communication range? To get the missing drone back, modern drones make use of GPS and tower-based internet technology together. The operator has already set the home location when starting the drone with the help of GPS. This way, the lost drone can safely get back to its home location. We hope you enjoyed decoding the complete drone working systems. See you in the next video. Before you leave, don't forget to be a part of our team. Thank you.